And then we're going to do a little bit of theory, and then I've got a page of calculations that we're going to do today. Yeah, that's good. So we had run through what adsorption and partition chromatography is, yes? Okay, did we get to ion exchange? No, I don't think we did. Here, the stationary phase is a resin that contains either anions or cations as the surface part of the stationary phase. And they're usually either sulfates or amines, protonated amines. So if it's an anion, they're typically sulfates that are tied at this end. That'll be a sulfite. Or they have protonated amines. And what they do is now, if your stationary phase, so the resin is the stationary phase. Now, if your mobile phase is negative, then it sticks to this stationary phase. If your mobile phase has a negative ion in it, it passes this through. And so if you think that I have a solution, and that solution might contain, let's say, sodium and magnesium, right? Sodium, magnesium. These are both cations. Only that's twice as positive as this one. If you run a solution through this right here, and it's got these sulfide anions in it, the sodium sticks to it, and then you can wash it off. The magnesium sticks, but it sticks harder because it's twice as positive. And so now your solution, as you wash it, the sodiums stick and then can be washed off, and stick and can be washed off, but magnesiums stick longer. They're retained in the column longer. And exactly the opposite for here. If I had something that differed in their anions, like a nitrate only has one charge, but a sulfate has two, sulfates would be bound harder to that resin than the other one. Okay. See a lot of that in inorganic chemistry. I'm sure it has biological applications as well. Not particularly something that straight organic chemistry is going to be interested in, because we're not going to have charged solutions that much. Okay. Then this last one. This one's a tiny bit counterintuitive. We're going to call this molecular exclusion. It goes by a couple of other different names. I see the biochemists mostly calling this size exclusion. Its twist on this one is called gel permeation. And in this case, I have a stationary phase that isn't just particles. They turn out to be like hollow shells. Stationary phase contains cavities. So if I did this, here's a stationary phase. And I'm going to try to elute through this stationary phase two materials. This is A, and this is B. Which one has the harder time? Yeah.
Are you saying like, do they have cavities or
No, not yet. I haven't introduced the cavities yet. This is still just regular packed column. B has a harder time because B has to make its way through here where A can slip through. Okay. Now, if I make these beads, instead of being full beads, if I allow them to have pockets, then exactly the opposite happens. A now passes through and gets stuck. And this is a complete over-exaggeration. My molecule B is not larger than the stationary phase, right? So just a complete exaggeration. But now what I'm going to see is my smaller molecules are more likely to be impeded because they get stuck, they get included into the stationary phase. It's only a physical process. I can wash them out, but it takes more effort. And so what happens in size exclusion is contrary to what you would get the other way around, is that small molecules are included into the stationary phase, and that retards their elution from the column. Retardation, we were talking in lab yesterday, is a word that we used to use in chromatography, but we're being told not to use that word any longer. So the small molecules get retained on the column, and it takes them a long amount of time to come off. Okay? And then affinity is just an open invitation. We can design this one to be kind of what we want. Affinity is selective. We can do things like, I'm not sure you have, this is how you spell it. I think immobilized has two M's. I think it does. Biochemistry takes things where we take a biological agent and then we tether them to a little plastic or resin bead. And now, you know, enzymes and antibodies and everything, they're very, very shape dependent. Well, if you've got the right shape, and I'm trying to wash you past this stationary phase, and you're the right shape, then you will stick to it. There's also an aspect here somewhere to allow for chiral separations. There's a fair amount of money to be made. If I have a racemic mixture, I've generated a reaction product that has more than one stereoisomer. Well, I want to separate them from one another. If I make my stationary phase be chiral, then we get different diastereoisomeric interactions, whether I'm the R isomer or the S isomer interacting with that stationary phase. And I can quite effectively separate those enantiomers. Okay, let's look at a couple of things that we have to talk about. And I think we might actually talk about them by doing, but at some point we're going to come back to this broadened line. Okay. Remember that we talked about, if that is the start time right here, that the time to get to the average part of that peak was the retention time. And we can use retention time for a number of things other than just columns and instrumentation. But this is how we're going to use it. So in lab yesterday, that was easy to quantify. And then we're going to talk about the shape of that curve as well. And there's a couple of things here that if I triangulate then that value is the width. That value is still the height. But at half height, I get another value of width. This becomes W half. Okay. And when a peak is just independent on its own, we might want to hear a number of parameters to describe it. We want to know how far it's traveled. And in the old days, what we would do is that this would be printed off a constant stream of paper on a roll of paper that had, you know, graph paper markings on it. And when the pen went down and you pressed the injection button, you would take a pen and you would actually physically mark the trace. And then it would roll, and then you would get the sheet. And so you would actually measure this in millimeters or centimeters. And then you would read that your chart was pumping out 10 centimeters per minute, and you would turn that distance into a time. Now, because everything's a computer, everything's computerized, we know what the time is just by checking. But, right, and height obviously is going to be, you know, if you've printed this on paper, it would be in centimeters or millimeters. Straight out of the computer, it would have just a response number, how much signal was generated by the detector. But here's the tricky question. What do we measure width in? Don't have to. You can measure that width as millimeters. But it's typical to measure width and width at half height as a unit of time. We're going to measure them in seconds. Can you think of any particular reason why we would measure them in seconds? Does everybody have access? Does anybody have access to the textbook? No. Okay.
I would be able to get it through some registry.
Yeah, me too.
I'm going to give you one piece of paper. That piece of paper has two sides. For those of you watching at home, this is the back side. It has a little table of equations that we're going to use, and then a picture on how to resolve two Gaussian peaks. When you look at the equations, at some point, we are going to divide retention time by width. And if those are in different quantities, if those are in different dimensions, then I have a complicated answer. But if my width is in seconds and my time is in seconds, when I divide them by each other, I get a dimensionless unit. That's fabulous. It means I just get a number. That's why we're going to do width in seconds. Okay, let's talk about a couple of the things that the experiment is going to generate for us. Retention time. Retention time is T subscript R. It's a lowercase t. If I accidentally wrote that as an uppercase T, what would that mean to the reader? Temperature. Temperature is a capital. Time is lowercase. So retention time is just the time that an analyte, somebody asked me yesterday what an analyte means. What does an analyte mean?
So it's been analyzed.
It's the thing being analyzed. Time analyte stays on column. It's the time it takes to elute. And we have a retention volume. Which is the volume of the mobile phase required to elute. Elute means come off the column. Here's where we start getting into a little bit of that. The retention time itself is subject to so many experimental parameters that we cannot just use the time that it takes to elute from the column as something that is going to predict what happens next. Okay. Yesterday we had 3 GCs out, okay, and all a GC is an oven with the coil in it, okay? And you put it in at one end and the sample comes out at the other, okay? What if the analyte that we were looking at on this instrument took 200 seconds to elute? That was its retention time. Could we feasibly expect that moving over to the other instrument would give us exactly the same time? No. What if this is at a different temperature? What if it's at a different flow rate? Remember, the carrier gas was below, we changed the carrier gas to blow at different pressures. We changed the temperature. What if the column length is a bit different? What if the column length is exactly the same in both, and it's exactly the same column, and it's the same temperature? It should be close, but I wouldn't put money on it that they're going to be exactly the same. They should be in the same ballpark. So what we're going to do is try and get to a relative number. And before we can get to that relative number, we're going to have to adjust the retention time. What the retention time measures adjusted is this. If I have a tube and I put A into that tube and I start the stopwatch here and and I stopped the stopwatch here, when A comes out, all I have is its time. What else is moving through the column? The carrier gas that is pushing the experiment along. How long did it take the carrier gas to get through? We don't know yet. So this is being pushed, we'll call it M for mobile phase. It is being pushed. Now the A sticks to the column and then jumps back into the stream and then sticks to the column and then jumps back into the stream and then sticks to the column and jumps back into the stream. Or if it's a packed column, zigzags its way through. But M just passes straight through. I need to know what that time is. So typically what we do is we take a small syringe of methane, that's a gas, it's hydrocarbon, it's natural gas, and we inject that and we count how long that takes to zip through. And so my adjusted, with the prime here, the adjusted retention time is the retention time that it took my sample to go through after I subtract the time that it took an inert carrier gas to get through. And we typically use methane as a proxy for that number, assuming that the methane just passes straight through, assuming. And that's going to lead us to retention factor. We saw retention factor when we did TLC previously. When we did TLC, what was retention factor? Here's a TLC plate. You put a little mark on the plate, you put it in a pool of solvent. The solvent was called eluent. And then the eluent moves, we hope, in a laminar fashion up the paper about 80%, 85% of the way up. And it drags the dots with it. And then we measured retention factor. Our book calls this K. There are enough Ks already in chemistry. We don't need any more Ks. RF. How did we calculate RF when we did TLC? It was the height of the spot divided by the height of the solvent front. We're going to do, and that became a relative number now, because if I said, oh, I think that was ibuprofen or aspirin. Remember we did separations of a drug, because it was 33 millimeters. Well, my ibuprofen didn't go 33 millimeters because everybody's experiment is unique. But if I take the ratio of how far my spot travels versus how far the solvent travels, the ratio between your experiment and my experiment should be the same. So retention factor is now going to be this number over that number. In TLC, our retention factors are all less than 1.0. In GC, they're going to be more. The numbers come out to be different. It's the same concept, but they come out to be different. separation factor, how far away are my dots from each other, or peaks from each other, or bands on the column? What is the separation? Separation is, some books are going to call this relative retention. And it is given symbol alpha. And alpha is the adjusted, which is that number right there, the adjusted retention time for one component divided by the adjusted retention time for the other. And the way that we write that out is that we always write the big number on the top, and we always write the number on the bottom. So alpha is always bigger than 1. Okay. Because the two things that you're comparing could be anything at all, which means that we need some kind of convention that tells us what's going on, and that is divide the big number by the small number. Yeah. We want that number to be big, right? If there's good separation, we want the number to be big. Can you think of a practical limit of how big we want that to be? I don't need a number. I just need a concept of. If I have really, really good separation between my peaks, so here's a peak, and then there's another peak right after it, I might want them to be a bit further apart. How about being this far apart? Because that's a really big alpha right there. This is fine, and you get to do another one after it. You get to free up the instrument so that somebody else can use it. Instruments are usually communal. They're usually shared between people. You want to do the best experiment you can in the shortest amount of time. So having all of this, all of these zeros here in the middle doesn't contribute anything to you. It's just, it's ticking somebody off because you're hogging the machine. Okay. Now remember distribution coefficient? We talked about it on the first day, that column chromatography had lots of things in common with distillations, fractional distillations, and it has lots of things in common with solvent extractions. It turns out that that ratio is also equal to the ratio of the KDs, the distribution coefficients. It works out to be just the same number. I don't think we're ever going to pull that in, but it just cost me 5 seconds to say it, so it's worth saying it. Okay? I don't think we're ever going to pull that in and use it. Okay, couple of other definitions before we do the calculations. Retention volume is given symbol, we could have written it here, is given symbol BR, and is the retention time times the flow rate. That flow rate is expressed as a volume. Flow rates can be, there's multiple different ways of talking about flow rates. You can talk about flow rates as millimeters per second, centimeters per second, and just have it be linear. And sometimes that makes more sense. And then other times we talk about volume. There is some calculation in this chapter about volume versus linear. And when I looked at the rest of the end of the chapter questions, it seems like that is not a big deal. So we'll take a very small look at it, but it's certainly not the most important thing. There's something about scaling that I'm going to leave to the last. And then here we go with our analogy to fractional distillation. Our analogy to fractional distillation tells us two things. Remember we call them theoretical plates? That when you have a fractionating column, every time you equilibrate between your mixture and you refine one of them further apart from the other, that was called a plate. And plates are actual real things in real distillation apparatus. But you can do the calculation to invent theoretical ones of them. The number of theoretical plates in a separation, N, is 16 times the retention time squared divided by the width of the peak squared. Because I'm doing time versus time, if I measure my width as time, I have a dimensionless number. I have a dimensionless quantity for theoretical plates, which means it's a number I can use for more than one application. I can use this for fractionating columns, I can use it for straight columns, I can use it for packed columns. What's my dentist called? I didn't even know I brought my phone with me. My apologies for not having it switched off. Okay. People, now that they know that you can do these little micro equilibrations in a column, want to know how much of the column you are actually going to use. So the plate height is something h is the length divided by the number of plates. And then we get to the useful part, which is called resolution. And you heard me throwing that number around quite a lot yesterday, and we're going to be looking at these pictures right here to look for what good resolution is. Resolution, which doesn't have an abbreviation. It's not R, it's not K, it's just called resolution. And this is kind of the important thing at the end of the story. And they've not given it a dimension yet. This is the change in retention time, the difference in retention time, divided by the average width. Now, that's great. What if we don't know how wide our peaks are? How would why and how would I not know how wide my peaks are? here is a peak, and then there's another peak. Here are my two bands. How could I possibly not know how wide they are? I triangulate, there's my width right there. Triangulate, there's my width. Some of the time, we're going to use the width at half height. And here's why. When that peak and this peak overlap, what you see is that. And my question is, how wide is this peak? We don't know, but we can say that it's this wide halfway up. Right. If we can now. Right. I can say that it is that wide halfway up its height. So we're going to use one of two descriptions for resolution. This is nice and simple. Or I'm going to use 0.589 times the difference in retention times between the two peaks divided by the average width at half height. Okay, let's do these questions. Some of them are easy. In fact, none of them are taxing. Some of them are pretty straightforward. They will just skip them through. Okay, so on your back page, so here's the front page, questions about tube dimensions, flow, retention time, and resolution. On the back page is a list of equations that we're going to use, and then a little diagram that tells us, using sigma, our standard deviation, whether peaks have resolved adequately or not. Okay, and it seems like from this diagram that an adequate resolution happens when alpha has a value of 1.5. At 1.5, when one peak ends, the next peak immediately begins. So good resolution is going to be any number that is larger than that. Okay? All right, let's do some of these questions. What is the volume of a tubular column with internal diameter 30 millimeters and length of 8 meters? How would we go about figuring that out? Yeah. Do you all have calculators? Because I know the answers to some of these questions. I think I have an answer to. Oh no, look what, I don't have an answer to the second part. The volume of a cylinder. How would we figure that out? If that is the length of the cylinder, and then this is the area at the base of the cylinder, then I need to multiply those numbers by each other. this is a circle. And the area of a circle is pi r squared. So I just have to figure out what I've got. And it tells me in the question that the diameter of that column is 30 millimeters. And that the length is 8 meters. Okay, small alarm bells should be ringing in your head because meters and millimeters are not the same unit. You're going to need to do a unit conversion. I typically find that it's easier to multiply up than divide down. I'm not going to convert 30 millimeters into meters. How many millimeters are in a meter? Come on.
8,000. Or sorry, 8,000.
There are 1,000 millimeters in 1 meter, so 8 meters is 8,000 millimeters in height. Okay, put the numbers in the question, in the equation, and come up with an answer. The other small alarm bell that should be going off in your head is that is an R and this is a D. Diameter is the width across the whole, from side to side of the tube. Radius is halfway from the center to the perimeter. So the diameter is 30 millimeters and the radius is 15. I only have 2 significant figures in my question, so I don't need to do pi to, we should though. Don't round it up. Don't round it to 3.1, right? 3.14159 will do, times my 15 millimeters squared times the length, which is 8,000 millimeters, gives me an answer. And actually, I don't have a number for this. I'm going to rely on you to figure that out. Talk to each other. Have a stab at doing it, and then talk to your neighbor, show them a number, so that's a good place to start, and then figure out, hey, I really did divide my diameter in 2 to find the radius, and then I did square it, and because that number is larger than 1, when you square it, it makes a big number. We're going to do 2 things before we write our answer down here in the box. we're going to decide what the units of our answer are, is. What's the unit for the answer? Yeah. Now you could, and you really, really probably should, do what?
Convert it back.
Back to what?
Meters.
No. No. What's much more useful than that? So what is my currently, the way that I've got it written out, what is my unit here at the end? It's in millimeters?
Millimeters cubed.
It's going to be in cubic millimeters. So volume is three-dimensional space. But what if I could make it be in cubic centimeters? What if I could do that? Why would that be more use than this? So we've missed a fabulous opportunity to do this question, this simple little question, correctly. 8 meters really is 8,000 millimeters. How many centimeters are in a meter? So instead of using 8,000 millimeters, I can use 800 centimeters. And how many millimeters are in a centimeter? 10. So my 15 millimeters radius just became, that was easy. And it gave me a volume that's now in cubic centimeters, which means I know what the milliliters are. And 1,000 milliliters is a liter. So this is going to be dramatically more useful for me. So this just became 3.152 times 1.5 centimeters, thank you, times 800 centimeters. $5,684. 5, 6.
5, 4.
Does anybody agree?
I can check.
Okay. How many significant figures are in my calculation? 2. I have 2 digits of precision here. I have 2 digits of precision there. I'm going to limit my answer to 2 digits of precision at the end. Okay? All right. If the stationary phase packing occupies 85% of this column, hey, it's a column, but it's packed. How much solvent, carrier gas / analyte can I fit into the column? Total volume inside the column is the volume of the stationary phase and the volume of the mobile phase combined, which tells me what I'm looking for. The volume of the mobile phase is total volume minus the volume of the stationary phase. I know what the volume of the station, of the total volume is, because we just calculated it. And we calculated it as cubic centimeters. But I'm gonna convert that into milliliters. It's not a conversion.
It's the same, right?
A cubic centimeter is a cubic centimeter is a milliliter. I'm just gonna write it, because this is a question now about volume. There you go. It's about volume. What's the value for the stationary phase number that goes there? How do I figure that? Yeah. That's my total number times 0.85. If I times it by 1.0, that would be 100% of the volume that's available. Well, I'm timesing this number, multiplying this number by 0.85, because it occupies 85% of the space. And then what goes in that box, I've got to decide. What's its unit? It's going to be milliliters. We'll accept cubic centimeters. And how many significant figures does it have? Still got two.
So these 806.
You could, instead of rounding that number up, 5700, you could go back to this and use those numbers. It might give you a tiny bit better answer right here, because you don't round up in the middle of a calculation, round up at the end. Okay. All right, let's do number 2. Let's find out what that is. I've got a mixture of benzene, toluene, and methane. Methane has been mentioned today. When did we mention methane? We calculate, it's a proxy for the carrier gas. The time that the methane takes to elute from the column is the proxy for what the total time to elute from the mobile phase is. So that's a ringer. I have C6H6, that's benzene. I have C6H5CH3, that's toluene. I have CH4. And these all have retention times. Benzene was 251 seconds. Toluene was 333 seconds. And methane was 45 seconds.
It's 42 seconds. 45.
It is 42, yeah. Okay. We talked about this. It's on the flip side of your sheet. The retention factor, it's called K here. So if you flip your sheet over, it says K equals TR prime divided by TF. That's the adjusted retention time. Which was your retention time after you've subtracted the time it takes the carrier gas, here's my proxy for the carrier gas, to elute from the column, all over the time that it takes the carrier gas to elute from the column, the mobile phase. So there you go. TR minus TM over TF. Which is for benzene, 251 minus 42 over 42. Just gives you a number. The number's 5.0. Do it for the toluene. What's the value for toluene?
The retention factor, I got 6.9.
6.9. That'll do. Anybody else get 6.9?
I do.
Okay. You do that by the 333 minus the 42 over the 42. Okay. So that's part 1. Part 2 says, find me the separation factor. Separation factor alpha is the adjusted retention time of the longest two elute of the analytes. I have two analytes, benzene and toluene. Which one took the longest time to elute? Toluene, so it goes on the top. We always set alpha up to be a positive number. Adjusted retention time is 333 minus 42 over adjusted retention time of 251 minus 42 equals
How does sig things work? Do they?
you have two.
Okay.
No, wait a minute. When you subtract or add, it only counts really if you have used the one that has the least number of decimal places to determine your significant figures. We don't have it. That's going to give you a 3-digit number divided by a 3-digit number, which technically allows you 3 digits.
So 1.39.
1.39. Comment on the value of the separation.
That's almost okay.
It's almost good.
Okay, how'd you get 1.39?
It should be like order of operations.
It's a thing I can't do it on my phone. Oh, I see what I mean by mistake.
Subtract the 42s before you divide them.
What I did, I took the TR, I took the 4.98 and subtracted by 42.
So what I would predict we have is that we have some overlap here. That alpha is less than 1.50. So there's a bit of overlap right there.
Is alpha and resolution the same thing on this one?
No, resolution is slightly different.
No, I just see alpha was 1.5. Where does it say that?
Oh, it actually does say resolution on the scale on this diagram, doesn't it? It doesn't say separation, it says resolution.
It says 6 standard deviations.
Yeah. Okay. All right, we're out of time.